In this video, we will design a differential scanning calorimetry experiment to measure the heat capacity jump at a protein unfolding transition, and we will estimate the required sample mass. We will look at it chemically, mathematically, statistically, and graphically. When a protein unfolds, its heat capacity increases. Graphically, in a heat capacity versus temperature plot, we observe a step upward near the melting temperature. The size of this step is the heat capacity jump, delta Cp. Chemically, you can picture the folded state as compact and the unfolded state as expanded. More surface exposed to solvent increases heat capacity. We will now build a clean diagram to show this concept without overlaps. We will design a differential scanning calorimetry experiment. The instrument has two cells, a reference cell with buffer, and a sample cell with protein in the same buffer. We scan temperature at a constant rate beta. The instrument measures the power difference needed to keep both cells at the same temperature. A jump in heat capacity appears as a step during unfolding. Graphically, heat capacity versus temperature looks like this. At low temperature, the protein is folded with a lower heat capacity. Near the melting temperature, the curve rises to a higher plateau. The vertical step size is the heat capacity jump. Mathematically, near the transition, the differential scanning calorimeter power signal relates to the heat capacity jump. If beta is the scan rate in Kelvin per second, m is sample mass, and delta Cp is the jump per gram per Kelvin, then the power step is approximately m times delta Cp times beta. We will use this to estimate how much sample mass we need. Statistically, we want a reliable detection. Let sigma sub p be the root mean square power noise of the instrument. A common design choice is a 5 sigma criterion. That means the power step should be at least 5 times sigma sub p. This gives a lower bound on the mass. Now, we will estimate the mass using realistic numbers. We assume a typical heat capacity jump for unfolding of about 1.5 joules per gram per Kelvin. We scan at 1 Kelvin per minute, which is 0.0167 Kelvin per second. Assume an instrument noise level of 2 microwatts and a 5 sigma threshold. We plug into the formula and compute. Practically, it is wise to include a margin and target about 1 milligram of protein in the cell. If the cell volume is half a milliliter, that is a concentration of about 0.8 milligrams per milliliter. This concentration gives a clear, low-noise step. Graphically, the expected power step equals m times delta Cp times beta. With 1 milligram, the step is roughly 0.025 watts per gram times 0.001 grams, giving about 25 microwatts. This exceeds 5 times the 2 microwatt noise, so the detection is robust. Statistically, averaging repeated scans reduces random noise. The standard error drops like 1 over the square root of n. This improves the precision of the estimated heat capacity jump and the melting temperature. Chemically, keep the experiment clean. Match buffer in both cells, degas the solutions, avoid aggregation, and scan slow enough for equilibrium. Subtract a buffer baseline before interpreting the protein signal. Summary: we designed a differential scanning calorimetry experiment to measure the heat capacity jump at protein unfolding. We connected chemistry to math and statistics and estimated the required mass at about 0.4 milligrams, recommending about 1 milligram for robust detection. A clean, baseline subtracted heat capacity step gives delta Cp and the melting temperature.